Hello, everyone. Welcome back to CSE 373. It has been a little while since I've seen you all. I hope you all had a nice little break and got to enjoy some time off. Today, we are starting our kind of last core topic for the quarter, which is this thing called sorting, the problem of sorting. In this video, I'm going to introduce some abstract terms and definitions about sorting, and then in the later videos, we'll talk about specific algorithms and how we compare and contrast them. So it's okay if this video feels a little abstract. I'm trying to set up some terminology that we're going to use throughout today. Now, before I dive into what is sorting, why do we care about it, I first have a couple announcements. So to start, exercise 4 is due this Friday, like the calendar says. And then on Friday, our last exercise, exercise 5, is going to be released, and it's due the following Friday. Now, the other thing that you have out right now is Project 4, which is due not this Wednesday, but the Wednesday after at 11:59 p.m. You should start this one early. This is one that can be really confusing since you have to navigate the code base to understand what's going on. So this is, like every project is a start early project, but this one's a bit more so than all of the others. So definitely be starting that now if you haven't. If you've already started, that's great. You're already ahead of the game. And we want you to start this one early. And the last thing is kind of the last thing after this course, after you turn in Project 4 and Exercise 5, is our last thing is Exam 2. So I want to quickly talk about Exam 2 logistics. By the time this video is posted, I probably don't have the exam logistics on the website yet, but they'll be there very soon. The good news is the exam logistics are going to be basically the same as Exam 1. So you have 48 hours to complete the exam it'll open Wednesday and is due Friday. But it really should only take a few hours. And usually, I mentioned this last time, if you're working with a group, it's totally okay if this takes you a little bit longer because communication's hard. This is not like in-person exam where you're just sitting writing by yourself the whole time. You definitely can work with groups, and that can sometimes slow down work time. But that's okay because you're probably learning a lot from that experience. So it's going to operate basically the exact same as Exam 1. It's open internet and notes, and you can work in a group of up to 6 people, and you're going to submit via Gradescope. I will put a clarification about office hours. I copied these slides from a previous quarter. We don't have lecture during finals week, so I'll mention about office hours later. So it's going to be released Wednesday of finals week at 8:30 a.m. and is due Friday of finals week at 8:30 a.m. So 48 hours later. We chose those dates because they overlap with our scheduled final slot. We felt like that was important because when you registered for the course, you kind of knew when this exam was. So you could start it early on Wednesday if you want to, or you can reserve the time for like our scheduled exam slot to work on it. This is not supposed to be like an actual 48-hour exam of nonstop work. We just give you extra time to accommodate your schedules. And like Exam 1, we don't have any late submissions. So the thing you're probably most worried about or most concerned about is what is the content of Exam 2, maybe less of the logistics because it's going to be very similar to Exam 1. Exam 2 is going to focus on the second half of the course. So everything that we left off with after Exam 1 and kind of all the way up through this week, this sorting topic. Those optional lectures that we had the past couple weeks where we had the weird holiday things, that stuff's not going to be tested, so don't worry about that. But kind of everything that was after Exam 1. Now, in some sense, I can't say the exam's not cumulative because you're going to need big O analysis. You're going to need to understand what a map is, what a stack is, what a queue is. But the emphasis on the exam is the stuff that we covered after Exam 1. So I'm really emphasizing testing those concepts. But yeah, the quarter builds off of itself. We've been using big O analysis the whole freaking quarter, so it's going to show up again. But we're not going to emphasize kind of the things that we emphasized already on Exam 1, since we already had you practice that for Exam 1. And like Exam 1, we're going to emphasize conceptual and why questions. So rather than just like multiple choice all the time. And unlike Exam 1, we might require you to write a little bit of code. And again, it's not going to be like at the level of the project because you already have the projects to test that code writing. But we might emphasize you writing a little bit of code to show your idea. So when you're thinking about studying, I would look into the lectures 11 to 24. Those are all the lectures that came after we said, oh, this is everything that's on Exam 1. That's starting way back when we talked about B trees and memory. and then going all the way up to this week where we talk about sorting. So sorting is the last topic that we're going to have on the exam. And then we have the corresponding sections, and then we have project 3 to 4 and exercises 3 to 5 will all be good things to look for. I will make sure that the topics list and the website is updated before our class on Monday this week. And please remember to look back at those learning objectives. Those should help guide you on what to study. Like usual, if you have any questions about this stuff, you could definitely feel free to ask. I'll reserve some time at the beginning of class on Monday to answer questions, and the TAs and I are always on the message board ready to answer questions if they come up. So there's that. Okay, so now I want to kind of switch gears a little bit and talk about kind of our topic for today, the kind of last topic of the quarter, sorting. So in terms of our learning objectives, we want you to be able to talk about this ordering relation and stability of sorting. We want you to be able to talk about these multiple algorithms, specific sorting algorithms, namely selection sort, insertion sort, and our last video we'll talk about heap sort. So in the sorting lectures that we're going to do today for Monday and Wednesday, we're going to talk about a lot of different sorting algorithms. So you're going to see lots of different algorithms that try to solve the same problem. In this video, I'm going to define what the problem is and properties about it. The next video, the second video, I'm going to introduce selection sort and insertion sort. And then in our third video today, we'll talk about heap sort. And we'll continue this learning 2 new algorithms on Wednesday's lecture, merge sort and quick sort. Now, you might be wondering, 5 algorithms for just to solve one problem? Why? Why do we need all of these different algorithms to solve the same problem? Well, sorting is a very interesting problem to solve. One is that intuitively, the problem itself is really straightforward to describe. Given a list of items, put them in order. And there's a lot of nuance into how you define order and how you write an algorithm to do that. So we study sorting partially because it's an incredibly common problem in programming. It's a very core component in a lot of algorithms. You remember Kruskal's that we talked about a few weeks ago? The first step was sort the edges. And we just said, ignore that. We'll talk about how to do that later. That idea of sorting your data shows up in a lot of places. And so since it's such a core problem, having many different algorithms that behave slightly differently and that there are trade-offs between is really important in designing a solution to whatever problem you're trying to solve. And additionally, since one aspect or one value that people get from this class, not the only value, but one value, is thinking about technical interviews. They usually care a lot about sorting. It's one of those kind of core things that we expect anyone that understands computer science to be able to talk about, because it's one of these core fundamental problems. And we like to talk about sorting, especially at the end of the quarter, because it's an interesting case study for how to approach computational problems. So we'll give some problem-solving strategies, thinking about how to design algorithms to solve a task, and use a lot of the data structures that we've talked about so far. So it's a really nice problem to work through because there are so many different ways of tackling it. We can compare and contrast and discuss the trade-offs for them. So we're really focusing on sorting this. So one thing I want to mention, just to kind of, you might have heard of this stuff, you might not, that's okay if you haven't. We're really going to be talking about these things that we call comparison-based sorting algorithms, which in some sense is just the standard way to sort. What I mean by that is you have your list of items, you somehow look at pairs of them in some sense and look at like, is this one less than this one? Algorithms that proceed like that, and all of the ones we're going to talk about this quarter, are going to be these comparison-based sorting algorithms. So this is going to be our focus. Now, I will mention there is this other class of sorting algorithms that there's no official name for them, but we like to call them the niche sorting algorithms that are hyper specialized to particular situations, and they don't work very generally. So what I mean by that is, for example, if you had a list of numbers and you knew that there are all the numbers between 1 and 5, there's no need to use this super general sorting algorithm that we'll talk about this week. You could just put them in an array of size 5, counting up how many 1s you see, how many 2s you see, 3s, 4s, and 5s, and then reconstruct the sorted output from that. That's okay if that wasn't clear how to do that, but the weird thing is that we assumed a lot about our input, and we came up with this hyper-specialized or niche sorting algorithm for it. We're not going to really talk about those. We're going to talk about this general set of comparison-based sorting algorithms. We just wanted to highlight this because you sometimes see that term comparison-based, because there are lots of other sorting algorithms, but the ones we're talking about today are the very core kind of foundational ones. So in order to talk about a sorting algorithm, we need to define what's the problem. So the problem of sorting is going to have, in some sense, a very abstract definition because it's a very abstract and reusable problem. So this is from Donald Knuth's The Art of Computer Programming. He defines sorting in very broad terms, where sorting is, in the intuitive sense, is just given a list of items, sort them. But you have to be a little bit more precise and kind of define what it means to sort something. And so Knuth kind of has this framework to think about, is the sorting task really relies on what we call an ordering relation, which is essentially being able to compare two values in the list. So you have some values A and B, you want to say, is A less than B? Now the ordering relation is just a very abstract way of defining that, because it's usually pretty straightforward. If you had, say, a list of ints, sort them smallest to largest, or maybe largest to smallest, whatever you want. But if you're given something like a Java class, like the movie class that has a name and a year, how do you sort that? Which movie is less than another? And the point here is to define this ordering relation abstractly, and it now lets it work in almost any situation. You, as the client of a sorting algorithm, get to define how you sort things. You might remember back from 143, the way we do this is implement the comparable interface. That's how we kind of define which item is less than another. But the sorting algorithm, from the sorter's perspective, doesn't care about the specific implementation details of which movie goes first. It just has an abstract ordering relation that says this movie is less than another movie, and you provide what that less than means. Now, these ordering relations have to make sense in some sense, meaning that they have to follow some rules. So Knuth outlines two rules that all ordering relations must follow. The first is the law of trichotomy, which means that only one of these things should be true. A is less than B, A is equal to B, or B is less than A. You should only have one of those statements be true in order for the ordering relation to make sense. And the other one that he defines is the law of transitivity. So if A is less than B and B is less than C, then A should also be less than C. A is less than B is less than. So these ordering relations need to kind of make sense from the perspective of trying to order them on a line. So now that we have this ordering relation, the problem of sorting a list is, given a list, a sort of that list is just a permutation or a rearrangement, changing the order of the values inside of it, of the sequence of elements that puts the things you're sorting by in non-decreasing order relative to whatever your ordering relation says. So a proper sort would have x1 less than x2 less than or equal to x3. Sorry, all those are less than or equals to. And so your sort, the final output, should have something like x1 first, then x2, then x3. So there may be many possible correct outputs for a sort, right? Especially if there's ties or something like that. But a sort is just one that doesn't break any of these ordering relations. The smallest thing comes first, and then the next smallest thing, etc. Now, and again, this ordering relation is supposed to be abstract because there are many ways you might want to sort a movie, and the sorting algorithm shouldn't be necessarily baked into only working with movies. So this ordering relation is a nice way of abstracting the problem and making it work in many, many situations. So that's our first definition, is an ordering relation. We decide how, or the client decides how things should be less than or greater than or equal to, and it should in some sense make sense by following these laws. And so it's up to the client to decide, how do you compare movies? The second definition we're going to need is one that we call stability. So for example, consider I have this list of artists, and they have a name and a year in them. So you might say, okay, well, how do you sort the list? How do you sort this? Well, there are many ways to sort it. Let's say we define our ordering relation to be based off the name. So it sorts them alphabetically based off names. Now, because there are multiple names, or the name appears multiple times for some people, then any ordering between those two should be allowed, because as long as you have all the Anitas first, and then Basia, and then Karis, and then Duska, that should be a proper sort. So there are two, or maybe potentially many, correct outputs from any sorting algorithm. All of the ones that just obey the ordering relation. And then maybe an implementation detail is how do you break ties. Now, that's all well and good, but we like to add one extra adjective, one extra description to some of the sorting outputs and not others. What we call a stable sort is one that, in the case of ties, preserves the original ordering. So both of these sorts here that I'm showing are valid, correct sorts. They put all of the Anitas first, then the Basias, then Karis, and then the Duskas. The difference between them is how they break the ties. We call the first sort stable because in the case of ties, Anita 2010 appears before Anita 2016 because Anita 2010 appeared before Anita 2016 in the input list. Just like here, Duska 2020 is before Duska 2015 because Duska 2020 appeared before Duska 2015 in this thing. Remember, the ordering relation we used here was only looking at the names. So in some sense, the year or everything else is completely irrelevant in terms of the ordering relation. And so all of this notion of stability is, in the case of ties, we preserve the original order of the list. And I really want to emphasize that both of these sorts are correct. They're both valid sorts. They just have, the one on the left has this extra property of stability, meaning it preserves the original order in the case of ties. You might be wondering, okay, why do we have this extra term? If they're both correct, why have this extra term for stability? Well, stability is a really useful property in a lot of applications. So for example, I teach, and so I work with spreadsheets of students a lot. So one thing that's nice is I can do is, because Excel uses a stable sorting algorithm, I can first sort my spreadsheet by name, and then sort my spreadsheet by section. Now, because the sort is stable, all of the students that tie, they all belong in the same section. If the sort's stable, they'll stay in the original order, the order I started with, which was sorted by name. And so now I can get you sorted by section, and within section, sorted by name, only because it's stable. If Excel did not use a stable sort, and I sorted by name and then section, well, as long as it put all the same people in the same section next to each other, everything else is out the window. And so stability can be nice in a lot of applications. Now, stability does, in some sense, kind of require more complex data. Like if you only had names and no years, you couldn't tell the difference between two entries that were Anita, then stability doesn't make as much sense here because you can't tell the difference between Anita and Anita. It's only when you have more complex data with extra fields do you actually kind of see the difference. So that's stability. We talked about the properties of sorting, ordering relations, and what a sort is. We talked about stable sort. And the last definition I want to kind of throw at us is talking about kind of the performance of sorting algorithms. We'll talk about lots of different sorting algorithms. As a reminder, when we talk about runtime, we talk about what's the runtime or the asymptotic runtime. What people commonly use is talking about time complexity. So that's another term they use for runtime or asymptotic runtime. So Dijkstra's has a time complexity of big O of E log V. Now, another useful construct that people think about is how much space is required. So all of the extra memory required to run an algorithm, we call the space complexity. Now, it's important to talk about the extra memory. So we're not going to be talking about the memory of the input. Like if you're given this list, we don't count that towards your memory usage because you're just given it. You're given it as a parameter. What we're concerned about is for your algorithm, how much extra space do you need? Do you create any new data structures that take up extra space? And so Dijkstra's has a space complexity of big O of V because we need to make that priority queue that's going to hold at most V elements. And we're going to have that dis2 map and that edge2 map. So it's going to use something like O of V space. But we don't count the space of the graph itself because Dijkstra's was given the graph as input. So that graph itself takes something like big O of V plus E space. but we don't count that towards the space usage of Dijkstra's because it already had to exist beforehand, before you called the Dijkstra's method. So these are the things we're going to talk about. In our next videos, we're going to talk about specific algorithms to actually tackle this problem. So we have kind of what is the problem of a sort, something, a permutation that obeys the ordering relation. We talked about one property, which is stability, and we talked about how do we analyze the performance of algorithms. In the next videos, we'll talk about specific algorithms to solve this problem.